Hi kids, it's Mrs. Fravel. How are you? Good, me too. I'm fine. Hey, today we're going to talk about how energy and matter flow through an ecosystem, including how organisms interact with each other for their nutritional relationships and nutritional needs, and some feeding strategies. So off we go. Okay. First, we're going to talk about nutritional relationships, and the easy way to explain this is who eats whom. Of course, there are several different kinds of feeding strategies or strategies to get energy, right? All living things, one characteristic of life is having to get energy, and they do that in two different ways. Autotrophs are organisms that make their own energy. And let's be clear on what we mean by energy in a living body. That's sugar. Living bodies are built from nutrients. The actual structures that build cells are made from nutrients constructed of chnops, right? But energy is also made of chnops, but it comes in the form of sugars. And that's what autotrophs build for themselves from the original energy source, which is the sun on terrestrial and shallow water ecosystems. This is photosynthesis, right? They use the sun and water to build sugar molecules, and they store those sugars for their mitochondria to then break apart for sugar. So we'll go through that more later. There is another source of energy in some ecosystems that don't have sunlight. There are actually ecosystems in dark places on land, in caves, and in the ocean. The deep ocean has no sunlight, but there are still ecosystems down there. There are still living things in those dark, dark places, and their autotrophs, their producers, make their sugars from chemical sources. So bacteria can use chemicals like hydrogen sulfide coming from volcanic sources of the earth to build their sugars. That's called chemosynthesis. So plants that use the sun build sugars with photosynthesis. Bacteria and some algae make their sugars from chemosynthesis. Okay. We need to have inputs of both energy and nutrients in order to synthesize that sugar. And these guys are the foundation of every ecosystem. They're called the producers in an ecosystem. Okay. Heterotrophs, I don't know where I'm going. I get out of the way down here. Okay. Heterotrophs are consumers, and heterotrophs include all animals and also fungi like mushrooms and molds. They have to consume energy in the form of sugars and nutrients that were synthesized by those producers. So these include, again, all animals, carnivores, herbivores, omnivores, scavengers, and then we have fungi that are decomposers. And then we have animals that we call detritivores or scavengers. Okay, and I'm going to just quickly go through these. You should already know them. This should be a review. Heterotrophs come in several different types. We have herbivores. They eat plants. The end. You know herbivores. Look at the cute bunny. There's also things like sheep, horses, giraffe, deer, gorillas are herbivores. Snails, a lot of snails are herbivores. And let's not forget the invertebrate animals, right? They're very important. Insects, there are a lot of herbivorous insects that eat plants, leaves, and also eat nectar and pollen from flowers, and they are food sources for other animals, right? And those are carnivores. Carnivores eat meat. Just by meat, we mean any other animal, right? So we get all kinds. We get fish like piranha. We get all of the felidae, the felines like lions. All of the canines, dogs, wolves, coyotes. And then, of course, there are predatory birds, predatory fish like sharks. This is a piranha. They're not as scary as people think, but still, carnivores eat meat. And then there's also the omnivores. These are generalists that eat anything. They eat both plants and meat. That includes in bears. Bears. Please note that I am kind of highlighting animals we might find in our ecosystem we're studying in Yellowstone. Okay. Also crows and ravens. These are very important omnivores. They are borderline scavengers. Pigs, Rats, chickens. Chickens will eat anything. Some dog species are also a little bit omnivorous, and of course humans as well. Okay. We also then have another kind of heterotrophic animal. These are detritivores and scavengers. Detritivores eat like dead, they just eat dead stuff. They're like the cleanup crew in an ecosystem. And then decomposers actually eat organic matter that has already been scavenged or eaten. So they are kind of the last stop for matter and nutrients, where they really break down all tissues in organic matter, and then they return the nutrients to the environment as byproducts. Okay, these are mushrooms, bacteria. Those are the decomposers. And they work on a molecular level to dissolve the tissue down to its nutrients. And then, of course, detritivores, we have stuff like earthworms, big megafauna type scavengers like vultures. Also, hyena are scavengers. There's a lot of scavenging birds. And then, of course, a lot of insects are also detritivores. They clean stuff up. In the ocean, detritivores include crabs, lobster, these jawless fish called lampreys and hagfish, and then sharks are also scavengers. Really, in the world, an animal will eat almost anything it can get its mouth on, right? Okay. All right. Excuse me. So what do all of those nutritional relationships look like in an ecosystem? We call them food chains, food webs, and ecological pyramids. And we basically use different models to show how energy moves through an ecosystem, because that's really what we're tracking, is how energy and matter move through an ecosystem. Okay? An ecosystem is a cycle. Everything affects everything else around it, and everything returns back to the environment at some point at the end of its life. Okay, so a food chain is the simplest path that energy and matter take through an ecosystem. This is just who eats whom. Okay, each level of who eats whom, there's a transfer of energy. When you eat something, you get its energy. Okay, the word trophic means energy, basically. So each level of transfer through a food chain is called a trophic level. Inputs into a food chain and food web are energy and matter. So energy originates from the sun on those sunny photosynthetic type ecosystem, and matter is macronutrients, including chnops, those big ones that we talked about last week. Okay, so these are our inputs that everything needs in order to survive. And what comes out of a food chain, the outputs, are also important. The energy leaves at each trophic level as heat. As an organism lives its life and does what it does, it loses energy as heat. Okay, nutrients, however, are a little bit different. So nutrients are stored in the body and used to build body structures, and also used in metabolic processes, but they kind of are returned to the environment by decomposition, either of waste products from an organism or from the organism's actual physical body when it dies. Okay, this is a fairly simple food chain. Of course, we have the inputs of energy from the sun. Water is also essential to life. This is what drives the first trophic level, which is always the producer, the autotroph in a food web, in an ecosystem. And then we get primary consumers like insects, whatever eats this producer. Its energy is then transferred into what eats it. So when we look at the arrows in food chains and then food webs, which I'll show you in a minute, the energy is represented by this arrow. Okay, the energy from the grass is going into the grasshopper. The energy from the grasshopper is going into the frog that eats it. the energy from the frog into the snake, from the snake into the hawk. And then this arrow is a little simple. Everything when it either gives off waste product, that's a really nice teacher way of saying poops, or when it dies, it is then, those nutrients from its body are then broken down by decomposers and returned to the environment where it is taken up by the producer, right? Plants absorb nutrients from the soil. Those nutrients in the soil get there from the dead bodies and poop that have been decomposed. Okay. What I want to show you here is the heat loss at each level. So each organism, as this grasshopper is hopping around munching on grass, it's releasing heat as a metabolic byproduct. So is the frog as it's hopping around trying to catch grasshoppers or get away from the snake. Every organism loses heat as it functions. Okay. So let's talk about these specific trophic levels. So the first trophic level is at the bottom when we build pyramids. And we're going to talk about 3 different kinds of trophic pyramids or ecological pyramids. The first one, the trophic level, is always the producers. That's at the bottom. So that's our producers: plants, algae, phytoplankton in the open ocean, and then chemosynthetic bacteria in the dark places. Okay. Second trophic level, those are our primary consumers. Those are herbivores that eat the producers. Okay. Third and up. So we have secondary consumers. These guys eat the primary consumers. We have tertiary consumers. Tertiary means third. Those eat the secondary consumers. They might also eat the primary consumers. And then sometimes, just depending on the ecosystem, we can have what's called quaternary level. This might be one more level of apex predator, okay? And those eat probably almost everything below it. Sometimes it's also an omnivore in that ecosystem. Okay. So remember, when you're looking at food chains, when you look at the arrows represent the flow of energy, not who eats whom, okay? Whichever direction the arrow is pointing, that's the way the energy is flowing in these food chains, okay? So in this one, lichen is eaten by slugs. Slugs are eaten by toads. Grass snakes eat toads, okay? The energy flows in that direction from lichen to slug to toad to snake, okay? From thistle to snail to thrush through to hawk, blah, blah, blah. You got this, okay? Sometimes, though, in the real world, food chains never exist as a simple line. The world's complicated. So we generally will represent who eats whom, or the flow of energy through an ecosystem through a food web instead of a food chain, because most organisms eat more than one thing, right? So in this one, this is very simple. We have producers as grass and a tree, right? This animal right here is an herbivore. It's a primary consumer. That's a deer. The deer gets its energy from both the grass and from the tree. It's a grazer and a browser, okay? This little chipmunk right there, or technically it could be a 4-lined ground squirrel, its energy goes to the fox. It also goes to the osprey, and it goes to, that's a hawk, and it goes to the owl. So every organism both consumes more than one kind of food and is also consumed by more than one predator. There are some exceptions. There are animals that do only eat one food. Pandas only eat bamboo. Koala only eat eucalyptus leaves. Fossa, which is a carnivore on Madagascar, they only eat one kind of lemur. There's also a snail kite that only eats one kind of snail. It happens, but it's rare. For the most part, again, animals eat many different things. Okay? All right, so how do we graphically represent what energy looks like in an ecosystem? How much energy is contained at each trophic level? Okay, these are models that show how the energy flows and how the energy is stored in an ecosystem. It shows the relative amount of energy or biomass or numbers of organisms at each trophic level in an ecosystem. And I'm going to go through each of those pyramids with you. The base of every pyramid, that's always the producers. Okay. And then each step up a pyramid represents a different level of consumer: primary, secondary, tertiary, quaternary, apex, however many levels you have in a given ecosystem. Okay. And it also depends on their nutritional relationships with each other. Okay, so the first one we'll look at is an energy pyramid. I'm just in the way. Energy pyramids compare energy used by producers and other organisms on trophic levels. Okay? So this is how much energy is moved from one level to the next level as organisms eat each other, are consumed. Okay? Now remember when I showed you the little heat arrows coming off the grasshopper and the frog and the snake? So that heat loss is actually quite significant. 90% of all of the energy in a body is lost to the environment just as they live their lives. That means there's only 10% of its energy available to be absorbed by the organism that eats it. Okay, so kilocalories or calories are a measure of heat on a very simple level. The energy that is in 10,000 kilocalories of grass, okay, it's absorbed the sun, this grass has grown, this grass contains 10,000 kilocalories of energy. As the grass grows and does its metabolic processes, it loses 90% of its kilocalorie value. So the rabbits that munch on that grass, they will only be able to absorb 1,000 of the 10,000 kilocalories that was in the grass. The snakes that eat the rabbit, they only get 100 kilocalories of the rabbit's energy. Okay, if we have 1,000 calories of rabbit, there's only 100 kilocalories passed on to the snake. If I have 100 kilocalories of snake, the eagle at the top of this trophic pyramid only can get 10 kilocalories from that 100 calorie snake. Okay, so we divide by 10 as we go from level to level. Okay. And again, 10,000 kilocalories of grass will be enough to support 1,000 kilocalories of grasshopper. 1,000 kilocalories of grasshopper is enough to support 100 kilocalories of frog. 100 kilocalories of frog is 10 kilocalories of snake and 1 kilocal of hawk. Okay? So you divide by 10 as you go up. We measure at the bottom how many producers do we have in an ecosystem, how much is supported at the base, and then we divide by 10 as we go up. Okay. And then we also can represent these relationships in a biomass pyramid. So instead of energy, we use actual weight, the weight of and mass of organisms at each level, and it's the same type of math. So if we have 1,000 kilograms of grass in a field, that 10,000 kilos will support 100 kilos of herbivores and 10 kilos of carnivores at the primary level or secondary consumer level, and that apex predator, there's only 1 kilo of it. Okay, so when we think about how the energy and the biomass tie in together, we get less and less biomass as we go up. Why is that? Okay, think about that for another minute and then we'll come back to it. We also have just sheer numbers. If we just sit down and count the grass, we can then do that same math, divide by 10 for each trophic level, and come up with the numbers that that grass will support. So 100,000 leaves can support 10,000 caterpillars. 10,000 caterpillars can support 100 blue tits, which is a bird that eats caterpillars. Listen to me. I'm in first grade. And then those 100 little birds can support one apex predator. Apex predators are pretty rare. Why is that? If we think back to the energy in the trophic pyramid, why do we have so few? It's because of that math, right? If we only get 10% of energy being passed on, there's literally just not enough to support more predators as you go up. The energy that's lost to the environment is just gone. And the result is that the predators don't have enough energy in an ecosystem to be as plentiful, as numerous as those lower levels. Okay. This is where that pyramid gets turned upside down. This is a situation that is man-made and is not a natural situation, but has influenced a lot of natural ecosystems. This is biomagnification or bioaccumulation, and this is directed at toxins in the environment, human-caused pollution in the environment. It runs the opposite direction from those other pyramids in that at each trophic level, it multiplies by 10 instead of dividing by 10. So if we have one part of a toxic substance in the water, the producers that live in that water and are absorbing nutrients from that water, they will end up with 1,000 parts of that toxin in their system, okay? So then we have the primary consumers that eat those producers. They are going to, as they consume and eat those producers, what happens is toxins stay in the body. They're really not good. And toxins are things like fertilizers, chemicals, plastics, oils, things that we don't dispose of properly that go into an environment. They're absorbed by the producers. And those primary consumers, as they consume that 1,000 part, it stays in their body, and they end up with, as a population, 10,000 parts of whatever that toxin is, okay? And then the secondary consumers that eat them end up storing 100,000 parts of that toxin. The tertiary and quaternary organisms on the trophic pyramid, they store those toxins at sometimes deadly levels, okay? We saw this back in the 1960s and 70s with a chemical called DDT that was used as a pesticide on farms for a very long time. What happened is it ended up running off into waterways, into streams and rivers, and when it accumulated at the top, okay, so fish-eating birds like ospreys and bald eagles, they the toxins stored in their tissues, and it caused a metabolic problem where the eggs that these birds laid had very thin shells or no shell at all, and the chicks were unable to survive. So that's why many of our top predators in ecosystems that are birds, they're endangered. This also happens with birds that eat other animals like deer and mice. They very often, when we put out mouse poison or rat poison, what happens is that that mouse or that rat may absorb the toxin and get eaten by a scavenging bird or a hunting bird before it dies, and the poison in its body will stay in that bird. And it might not be enough to kill the bird, but if that bird continues to eat poisoned mice, it will accumulate in its tissues. Okay, and so we see this problem across all kinds of predators. Biomagnification, you multiply by 10 as you go up, and it's terrible. Okay. All right, one last thing. So what happens in a pyramid, if any level is removed. So what happens to the entire ecosystem if we remove one level of a pyramid? Give you a second to think about it. Okay. And by removal, I mean the organisms that fill that level are gone. They're either extirpated, which means they're locally extinct, or they are extinct as a species. Okay. What happens in that case is that the trophic level above that level that has disappeared, they will also start to disappear, okay, because their food source is gone. The trophic level below that level and any competitors that that organism had on its same level, they will start to increase because their predator is gone, their competition is gone. What happens is we get an imbalance in their population, and they may start to overexploit their niche. So think back to the video about the Yellowstone wolves and what happened with the elk. And that's actually going to be part of your assignment today as well, is to read a little bit more about how trophic cascade happens in the real world. Okay? We generally will only call it a trophic cascade if it affects 3 different levels of a trophic pyramid in an ecosystem. Sorry, I'm going to get a drink. Hold on. Ooh, okay. Okay. So that's it. Your assignment for today is on Canvas. You have a couple of things. I'm going to make another video that will show you how to complete the Yellowstone Food Web assignment. It's 2 different documents, 3 different tasks, 4 different tasks. So make sure that you are following the directions, watching the videos, read all of the things. Okay, all right, you guys are awesome. Also, don't forget to, if there is anything in this little video and anything on your assignments that might help you support the evidence for your claim, or if you need to update or change your claim on your CER, don't forget to do that because we're almost done with this unit. You're going to be turning in your CER next week. Okay, you guys are awesome. Let me know if you need anything, and have a beautiful day. Wear your masks.